I know some people are still hopping on, but we will go ahead and get started with the introductions here. My name is Katie Caskey, and I am the current chair of the CTS Transportation Education and Engagement Council. And just a little bit of background on the councils. CTS councils provide a forum for transportation professionals and researchers to exchange information on current transportation issues and trends. They bring together university faculty and staff with practitioners from the public and private sectors to recommend direction and participate in improving the center's research, education, and engagement programs. Sam from CTS will be sharing, if she hasn't already, a link in the chat to more information on the councils. Today's webinar features a presentation on preparing transportation professionals for AI integration, and we hope that this is the first of two webinars we'll be featuring about AI in transportation, with the next one being held in early 2026. And I'll share more on that in a moment. But before I do that, I'd like to turn it over to my council vice chair, Amber Cameron, who was co-facilitating this webinar with me. And Amber, will you like to introduce yourself and explain a little bit more about the webinar?
Great, thanks, Katie. Hi, everyone. I'm Amber Cameron, and I work at the University of Minnesota in the Office for Public Engagement. And I'm lucky to serve as the vice chair of CTS's Transportation Education and Engagement Committee. So thank you for joining us today. A couple of housekeeping items before we get started regarding Q&A. Throughout the webinar, if you could use the Q&A function at the bottom of your screen for any questions or comments that you may have. Or you could also use the raise hand feature. And depending upon where we're at in the presentation and how we're on schedule, we could unmute you so that you can ask your question verbally. Myself and some others will continue to monitor the Q&A and have opportunities to address questions throughout the webinar. Also, if you are attending this to receive any sort of credit for continuing education, this provides 1.5 professional development hour credits and 1.5 American Institute of Certified Planner certification maintenance credits. A form will be uploaded to the chat for anyone who needs this, so feel free to take advantage of that if that is helpful. And just a little preview of upcoming things this winter. CTS hosted several Research Council webinars this fall, and you can find all of those recordings on the CTS website. So in addition to this wonderful group of people, feel free to check out additional webinars that were hosted. And then finally, if there are any students who are joining us today, if you could send a chat to all panelists with your name, we'd love to track the students who are here, both the number and who you are, so that we can continue to support you in opportunities through CTS. So with that, I'll turn it back over to Katie. Thanks.
Amber. And just a note that the CTS staff members, James DeSoto and Sam Han-DeVille, are also on the webinar supporting the event, and they will be helping with a lot of the logistics in the background. So just a quick reminder about what this webinar is before we dive in. And it's really that artificial intelligence is rapidly reshaping how we design, plan, and manage infrastructure systems. And in this webinar today, we'll discuss how AI tools are beginning to influence teaching, research, and professional practice in civil engineering. The conversation will touch on how the field can adapt curriculum and training to prepare future engineers for AI integrated professions and explore questions around quality management, professional ethics, and community-centered design in AI-driven context. And we'll also hear insights from MnDOT's ongoing AI pilot identification project, offering a practitioner's perspective on how state agencies are evaluating opportunities and risks associated with AI implementation, and how agencies are engaging and educating staff about AI. So hopefully that matches what you were expecting today. And just a note that today's webinar is really focusing on AI in the Minnesota context. And our early 2026 webinar, we're hoping to have one that focuses more on a national and international context around similar topics. So stay tuned for that or in early next year. And so with that, I am pleased to welcome today's speakers. I'll give a really brief introduction of them all before we kick off. They can provide additional context about themselves as well during their presentations. So our first presenter is Dr. Choi, who's an professor in the Department of Civil, Environmental, and Geoengineering at the University of Minnesota. Melissa Barnes is a licensed civil engineer with over 21 years of experience in transportation. She works at MnDOT. And Dr. Qizhi is an assistant professor in the Department of Civil, Environmental, and Geotechnical Engineering at the University of Minnesota. So with that, I am going to turn it over to Seongjin, who will kick off our presentations.
You see my screen?
Yep, you're good to go.
All right. Hello, everyone. My name is Seongjin Choi. I'm assistant professor at the Civil, Environmental, and Geoengineering Department at the University of Minnesota. Um, so my whole expertise is how to apply AI in for transportation system. And I have been working on applying AI, developing new AI models for transportation problems since I think 2016. So if you're looking for someone who has 10 years of expertise in AI transportation, you're looking at that person. So today, I'm going to briefly introduce about how our department is considering AI education and how we are developing new courses so that we can foster new generation of civil engineers, civil, environmental, and geoengineers who understands AI and then knows how to apply AI for real world problems. So before we go into the details, let me bring up why AI education is an urgent priority in transportation or broadly in civil engineering. So one of the reasons why is because it's reshaping not only transportation but many different industries, and specifically for in transportation context, AI will reshape how we design, operate, manage transportation systems. And I'm pretty sure Melissa is going to introduce more into the detail, but private agencies and entities are already piloting AI for operations, maintenance, and planning. And there have been a lot of research going on of how to apply AI in those kind of aspects. But to do so, we need new kind of skill sets. So practitioners or researchers need more AI literacy, which means that it requires fundamental understanding of AI, and then they need to understand how AI works to make proper decisions and where to apply AI. So to answer that call, our department in UMN CGE is integrating AI into the curriculum to bridge the gap between academia and practice. So before we go, I want to kind of define my perspective of AI. So I'll start from AI. So AI is not a new topic, to be honest. So AI, the first term or first occurrence of AI emerged as soon as computer was developed. So in one paper that Dr. Alan Turing published in 1948, already mentioned about whether a machine can think or not. So AI in general can be defined as any kind of effort that tries to make machines or computers mimic human intelligence. So this is not a new topic, and it's been there for more than 4, 5, 6 decades. But it became more kind of famous or popular as soon as the themes related to machine learning came up. So machine learning can be defined of using any statistical methods to teach machines to learn from data to be good at some specific task. So before machine learning, there were many different types of AI, usually using some logical representation to define how AI should work. But then the difference here is to teach machines to learn by themselves by looking at the data. And one of the early successful example of machine learning is spam filtering. When emails first came out, and then there were a lot of ham emails and spam emails, machine learning was applied to identify spam emails from ham emails. And around 2012 or 2011, there was this new term which was also kind of studied over the last few decades to try to use deep learning, which can be defined as training machines to be good at complex tasks based on neural network and massive data. So now the difference between the machine learning and deep learning is that we are using neural networks, which is kind of benchmarking how human brains work. So we are designing artificial neural networks to learn the data, and then we are using much more data than we used to do when we are using machine learning. So I give this example of relationship between AI, machine learning, and deep learning. So if AI is a food, machine learning is Italian cuisine, and deep learning is vongole pasta. And as you can kind of figure out, there are AIs that are not machine learning, and there are machine learning that are not deep learning. So if you are making decision on how to invest your money to develop new type of AI technology, you should be able to know what is the difference or whether the product you're investing on is AI or machine learning or deep learning so that you can make a proper decision. And nowadays there's new concept, or it's not a new concept, but new trendy word called generative AI. So generative AI technically sits right here where it's kind of because generative AI, the concept existed way before deep learning. It was called as generative modeling. But then nowadays, it's within deep learning where we are trying to teach machines to create new content or new data by learning patterns or structures of the data by using a lot more data than we used to do with deep learning. Kind of coming back to the why question. So why AI education is necessary in civil, environmental, and geoengineering. One of the most important reason we are thinking of is that when it comes to really building AI that's helpful for the entire industry, it requires three different aspects. So one is computer science or coding, programming. The second part is understanding how AI works in terms of mathematics and statistics. But also there's there's big area where we have to understand what the problem is. And then by understanding this domain knowledge, we can actually build AI that is actually helpful. And this is primary reason why we think that we need to have AI education specifically designed for civil, environmental, and geoengineering. I'm not sure about the audience, but if you're kind of familiar with uh, education system or our courses offered to the undergraduate students, these are the two courses we use to teach programming, numerical methods, so probability and statistics. And the two pilot courses that we are offering in AI world is kind of building on top of these two courses. So the first course that I taught in spring 2025 is called Applied Machine Learning for Civil, Environmental, and Geoengineering, which teaches applications of statistical machine learning and deep learning in civil, environmental, and geoengineering. And kind of building on top of that, I'm teaching this course called Generative AI for Transportation Research, where I teach deep generative models or LLM, large language models, large multimodal models, or large reasoning models that can be applied to transportation in general. And we hope other faculties, not including myself, are trying to build or trying to develop new courses that are specifically for each specific research domain. So here, Dr. Qizhi, he's specializing in structural engineering, and I believe he's going to offer some course related to scientific machine learning in structural engineering. There are other faculties in water resources or environmental engineering who are interested in developing more topic-focused courses in the future. So the way we teach, or the way I teach these two courses is in threefold. First, I teach the students some fundamental theory or concept so that they can learn the fundamental principles. And then we do some practice lab, or I offer homework assignments so that they can apply this new knowledge or new concept in hands-on sessions. So that I lead a coding session where I teach students how to code machine learning models or deep learning models or generative AI models for transportation specific problems. And then by accumulating that experience, students identify real world problem by themselves and then solve those problems with AI. So to kind of go into the details of those two courses. So in the first course, the applied machine learning for CGE, I'm teaching three different aspects. So first, I start from classical supervised learning, which is machine learning, including linear regression, logistic regression, or other topics like support vector machine, Gaussian process, or decision tree, random forest, etc. And then we are going into the deep learning world where I teach neural networks, computer vision, and sequential modeling. And then I wrap up the course with emerging topics such as physics-informed machine learning and generative AI. So I'm really starting from this outer edge of the circle and then going into the center where where there are new things or new concepts to learn. And these are some examples of the lab sessions and the homework assignments I give. So because this course is designed for general civil, environmental, and geoengineering students, so we have examples not only from transportation but also from environmental engineering or structural engineering. I also collaborated with other faculties in different research fields to identify specific areas where machine learning can be applied. So here, one example is factors influencing urban heat island, where we use logistic regression or where we use linear regression to identify key factors influencing the urban heat island effect. And we have two examples from transportation. The first one is travel behavior modeling or mode choice prediction, where we use logistic regression to predict which mode a person is going to take based on their demographics or proximity to bus stops and etc. And then students kind of identify whether so students have to write a report on whether having some kind of policies kind of benefiting or giving credits to using some sort of public transportation system is going to be actually helpful in terms of decreasing VMT, for example. Also, we are using computer vision to detect vehicles and pedestrians. So I'm using that example as one of the homework session where students have to develop new model to identify vehicles from video and then track so that they can extract vehicle trajectories. And here are some examples of the student course projects that actually came out from this course. There were one student from transportation, so she did a project related to lane changing prediction. And there were other projects, especially in environmental engineering side. There were someone who did algal bloom prediction using machine learning. And there were some emphasis on structural engineering, predicting responses to structures from earthquake or predicting steel or concrete strength using machine learning. And in the second course, which I'm teaching, which I taught this semester, is called Generative AI for Transportation Research. Here I teach very detailed or very specific topic, which are deep generative models and large foundational models, where students learn how those models that we use from ChatGPT or image generator that we can use, how they work, and then how those can be applied to transportation research problems. So some examples of lab sessions I'm doing is, one of the first lab session I'm doing is generating household travel survey data. So students are working on tabular data and then training generative model to synthesize or generate synthetic population based on the survey data. And the second example is generating highways traffic flow dynamics. So here we are generating this whole figure of time-space diagram or speed contour so that so that we can replace or we can potentially replace traffic flow models to predict congestions or use it to identify the congestion early in the traffic flow stream. Also, we are using generative models to predict vehicle pedestrian trajectories. Um, uh, and because generative AI in general are doing some kind of probabilistic prediction, we are applying that idea so that we can predict the distribution of these trajectories. And here are some examples of student course projects that students presented this semester. So there were two students who were working on anomaly detection. One was working on pavement temperature profile data to identify whether generative model can help identify those subtle anomalies in pavement temperature. Another student did a project on identifying anomalies from traffic detector data. And there were some students who worked on trip generation, activity sequence generation, or tabular data generation, where they used some kind of survey data or other third-party smartphone-based data to predict or to generate new synthetic population, synthetic trips, so that they can use it for planning purposes or other sorts of applications. And because of this new trend of having a lot of tools such as ChatGPT, there was a lot of interest in applying or developing ChatGPT-like system for transportation tasks. So there were three projects applying vision language model or large language models for transportation applications. So first one was doing some kind of classification. The second project was doing trajectory prediction, but explainable trajectory prediction. And the third one was doing um, a traffic management system aided by large language model. And in class, I think this was kind of unique to all students in my class. So I let students to use generative AI or any AI tool to for any kind of purposes. I had a lot of consideration to make this decision, but I felt it's kind of contradictory to teach students AI and generative AI, but not letting them to use those tools. But then I let students to take make the students to take the full responsibility on fact checking and reviewing any form generated by these AI tools. And the students have to cite or make a statement that how they used these tools in their reports. And in general, I'm very satisfied with the outcome because students were very responsible of the tools they were using. And then because many students in civil engineering, they are not very well trained in terms of like computer programming and etc. But these tools can actually help them in terms of writing code so that they can only focus on the important part where it's the actual problem they are trying to solve. So actually, I think it was kind of effective in general in my course. I'm not sure if it's going to be effective for other courses in other departments or in undergraduate education, but at least for my courses, these were effective. So to kind of conclude my talk here, so our goal is to cultivate a new generation of transportation professionals who can not only use AI tools, so anyone can use AI tools, but also we want them to think critically about their application and lead innovative projects and shape the future transportation systems ethically and effectively. And specifically, we want them to be critical thinkers who can understand how and why behind AI models and innovators who are equipped to pilot and implement AI solutions by themselves for real-world problem without relying on other computer scientists or other people who are only specialized in AI, and to be leaders who will define the next generation of transportation technology because it's changing so fast. So we need to we need to define what it's going to be in the future. So I guess that's it for my presentation. So if you have any questions, I'm happy to answer.
Great. Yep. There are a couple of questions in the chat. One is someone is wondering if people not at the University of Minnesota can sign up for the ML course in transportation.
I have no idea.
Okay.
I have no idea how that like administratively how that works. Um, there were there was one student who were auditing, but he was also from the department, and there were two students who are auditing the generative AI course. But those two students are visiting students from other university. So technically, if you show up, I don't mind. But administratively, if you want that to be counted towards some kind of credit or something like that, you also need to talk with the administration office of the department or the university.
Okay, wonderful. And then the other question is, do you anticipate that these new courses in machine learning and generative AI modeling will require any additional prerequisites in addition to the courses that are generally part of an undergraduate CE curriculum?
I don't, so as far as I understand, these courses are not required. So, and I don't think these are going to be required courses. So I don't think there will be changes in the course requirement in civil, environmental, and geoengineering curriculum. But these are more like a design course where we have students, if they are willing to take this course, have them understand these AI and machine learning tools, so that they can apply to real world problems.
Wonderful. Any other questions before we move on to the next speaker? You can type it in the chat or raise your hand. Okay, Katie, I think we can move on to the next speaker.
All right, I think Melissa, you're our next speaker if you want to pull up your slides.
Can you verify you can see them?
Yep, we're good to go.
Great. Thank you all. I am as I was introduced, my name's Melissa Barnes. I work at MnDOT, actually in our operations division, which is about 3,500 of MnDOT's 5,500 employees. So my background is as a civil engineer is in program delivery and traffic engineering. But right now I'm working on a special assignment to help deliver AI pilot projects within just our operations division. For context, we have a MnDOT-wide AI working group that I'm a part of and is delivering some of the more broader MnDOT AI specific pieces at MnDOT that I'll talk a little bit about. So as I said, we're working on putting some AI pilot projects in place. So why are we exploring AI right now? We know that it's changing how people work and how agencies deliver transportation services. And we know that AI has the potential to increase our productivity and expand our capabilities in this space, but it also comes with risks. So we're really wanting to take this thoughtfully and explore how AI could be used across our division and ensure it's integrated responsibly. Um, so it needs to fit into MnDOT's goals. So the goal of any MnDOT AI application is really to enhance how we do our work and not replace folks' roles, but implement projects that do things like improve safety, efficiency, and responsiveness to the traveling public, which fits directly into our mission and vision. So you can see from the slide here that we are kind of still mid-project. We have done a national scan. We saw what other transportation agencies around the country were doing, and we've collected staff ideas via a survey. We are working on prioritizing those ideas based on a host of things I'll talk about a little bit more. And then we're really looking to do some pilot implementation, fund those small scale projects, talk about upscaling, do some evaluation. And yeah, well, it's exciting. There's already some AI projects really going on at MnDOT, and I'll talk a little bit about that too, but that's where we are in process. So in order for you to understand though, right, I talked about I'm just in operations. I want to give a little bit of a broader MnDOT context. Talk a little bit about what's going on in other parts of MnDOT. So in this July, MnDOT actually released a generative AI standard. So Copilot was released this summer, came along with this generative AI standard. So Copilot is secure within MnDOT. Our employees are able to use it, and that is the program, the large language model that we are able to use. And then it also has some discussion of ethical AI use. So employees must practice responsible AI use and using it as a supplement and not a replacement for human judgment. Similar to what Seongjin just talked about, you have to check the work, you're responsible for it, and that just because it came out of AI, you don't have an excuse that it wasn't checked. We also have some considerations for citing AI when it's used to create information. We feel like that's a little bit slipperier. You should probably do that if you really haven't changed it, but if you've used it more as a spell check or to check your information or to help with brainstorming, maybe not the same thing. Our folks have created our own internal training for Copilot. So these are the Copilot courses. They are able to be taken by anyone at MnDOT. They're about an hour each. And we've had really good attendance and really good interest in them. During the course, the large chunk of the meeting is really spent on question and answer sessions and live troubleshooting and working together on problems so that folks can come to the classes, which are held basically every week, and able to troubleshoot issues, ask questions, learn a little bit more about how to use Copilot effectively. We're also on the other end keeping track of use cases and issues that come out of these courses and feeding those back to Microsoft or solving them in another way. So pretty nice. Now, a little bit back to how we're talking to our employees and talking to folks at MnDOT about artificial intelligence. We find a lot of times in order for us to even get to idea generation or get to, okay, let's talk about what issues you have that we could solve with a pilot project, we really need to ground folks in shared definitions. So we have to do some definitions of what we're even talking about with artificial intelligence. So I typically start with a little bit of history. I know there's a lot on this screen, but it's really talking about in that the term artificial intelligence has actually been around since the 1950s. So it started with those early computer developers, if you've ever heard of Alan Turing and the Turing test, starting to get to, okay, if you could trick a human into knowing whether or not it was dealing with another human, but it was actually a computer, that would be kind of an artificial intelligence test or a test for human intelligence. There's been lots of different things in our lives that really are artificial intelligence, Roomba, Siri, Alexa, so lots of things. The other thing I try and get across to folks as we're talking about this is that media often shapes our views and influence of what artificial intelligence is. So things like since the 1960s. So this is HAL from 1968 to 2001, A Space Odyssey. We know the Terminator, that was 1984. We've got Arnold Schwarzenegger up there. And then our kids too. Our kids see things in their movies. So Wall-E here back in 2008, another dystopian universe where robots had kind of taken over and were running Earth. I also have an onion diagram, Seongjin, so kind of funny. This is part of how I talk about artificial intelligence and set expectations about similar definitions. So again, similar to Seongjin's, I'll go through this pretty quickly. Artificial intelligence is just any technique which enables computers to mimic human behavior. Machine learning, which is an algorithmic learning designed to learn from data without being explicitly programmed. Generative AI, which is anything that generates text, images, or other media. And then large language models, which is really what's capturing, I think, a lot of the media and a lot of folks are hearing about outside, like ChatGPT, Copilot, and DeepSeek. Another thing that I think is important to get folks thinking about what kind of pilot projects or what kind of ideas might be possible is really providing DOT related examples for people to understand where benefits can come from. So things like smart traffic control and congestion management or predictive maintenance, visual recognition, estimating, maintenance parts tracking, scheduling or routing. I mean, we run snow plows, crash safety analysis. We're already doing some of these though. So although we're looking to pilot more projects, there are already projects with AI integrated or as a really big part of the software we've already purchased. It's honestly hard to avoid. And I would say I'm only showing you one of these slides due to time, but I have 3 or 4 of these slides and I could make dozens more. It's kind of like drinking from a fire hose. So again, we're trying to be thoughtful, pointed, and think about where it's appropriate to use AI as we start to integrate some of these projects and some of these products. This is another slide I like to show. I think one, yes, it's funny. There was an AI prompt you can find. Somebody said, show me salmon in a river. But I also think it's really important to be very honest and open about the challenges of AI. Bias and fairness is a real issue. If AI is trained on skewed data, which the internet has its own brand of skew, you are getting back skewed data. So AI can also act a lot like a black box. And as folks who are trying to deliver products that are reliable, that are understandable, that we trust, it's really hard to understand all the time how AI makes decisions and therefore trust it to be able to use it in the real world. Privacy and data security is an issue. We work with private data. We can't be just putting that data into AI models and not understanding how it's being used or where it's going. We are concerned about the workforce impact. We talk a lot about augmenting our staff, helping folks, getting the drudgery out of work, doing things we haven't been able to do before that will assist the traveling public and make things safer and better. We know there are regulatory gaps. A lot of these companies that are operating artificial intelligence models and large language models are being sued due to copyright issues. Errors in learning how to use AI. This is a big one and a big reason we have the training, making sure that people stay skeptical, are constantly checking all the work. And we're also worried about environmental impacts as we are part of a state who wants to make sure that we're being responsible and responsive to those issues. So all of those put together, again, starting small, being thoughtful about how we integrate AI is really important at the DOT. So we back to the pilot projects, pivoting again. The survey was really done to help develop the pilot projects that address issues and not just say, hey, AI is the answer, where's the problem? But really dig into what problems people are experiencing, asking folks what data they can't currently tackle, where is their drudgery or things in your job that just make it hard to get done. Things that are really repetitive that if they were cleared up, you would have time to do other important things. So just quickly, like I said, we had the why MnDOT is exploring AI as we put together this survey. We provided background info, the information I just kind of showed folks before. Some of that information was provided directly as background educational information. So people could just say, oh, okay, this is what they're talking about when they're talking about large language models. This is what they're talking about when they're talking about machine learning, and trying to get folks thinking. So it was a long survey. We let folks really stop at any time and broke it into 3 sections so people could say at some point, I don't really feel comfortable going any further. I don't have a lot of experience with AI, so just stop there. I want to point out section 3, where we got some examples from around the country and asked people to kind of rate those examples. I also thought it was really important to give that to get a taste of what AI can do and not just ask people to guess at what kind of problems it could solve after a really brief introduction to artificial intelligence capabilities. A lot of these sections were open-ended, so people could express their full thoughts and ideas and concerns and excitement. So we had a lot of rich data and rich responses back. So talking a little bit about the usage, excitement, and concern, we only got about 200 people to take the survey. Like I said, MnDOT has about 5,500 folks, but actually we still generated hundreds of ideas, literally hundreds. So the people who did respond had really rich, really a lot to kind of talk about and really good idea generation. So we definitely have a lot to move forward on, and it's still going to be hard to make decisions on even what projects to kind of prioritize first. So from a familiarity perspective, we really got probably about 60-70% that feel pretty familiar, somewhat familiar or very familiar, and the rest either not familiar at all or really not sure how it would mean for their work. For excitement, you really have about half of folks who are pretty excited and half of folks who are either don't have an opinion or are not excited at all. Same with concern. You get about half of people who are somewhat actually, it's more like 75% who are the very or somewhat concerned, and then 25% who are not at all concerned or really have no opinion, which I think is a good place to be. It's good for people to be cautious. Yes, there's excitement, but also married with that caution of this is a really big opportunity, but I need to be thoughtful about how it's implemented. So overall thoughts on how we might use artificial intelligence. Many folks see really high value with artificial intelligence assistance, and we should be responsibly integrating technological advances and not fall behind. Folks ask for even more training and guidelines and hands-on workshops and really hit on that gradual adoption. Others highlighted the downsides, the environmental impacts, potential water usage, concerns about the accuracy of AI outputs, concerns about employees without strong technical expertise that rely too much on AI, and concerns about skill deterioration. So really pointing us again towards that gradual adoption and thoughtfulness about how we bring things together. So again, like I said, we had hundreds of ideas folks brought together. They kind of fell in these buckets. So people mentioned things like scheduling meetings and classifying documents, flagging errors in plans, searching databases. We have a lot of data at MnDOT, so more effective searching and ability to organize that data is helpful. Cost estimates, data transformation, folks who have to take data from one system and change it a couple times to put it into another system, workload tracking, near miss detection for crashes, analyzing public comments, and a lot of chatbot ideas. I'm going to skip the next slide here for time. This one, so this is what we're doing right now. We're really looking at prioritizing the ideas that we have and putting them into kind of, and talking about which projects might be feasible and reasonable to move forward. So things like performance of similar projects, transparency and bias. We really want to talk about impact on skills and safeguards, privacy and data protection, efficiency gains, and definitely alignment with MnDOT's goals. And then IT readiness and startup costs, things like that, in order to see what we can kind of look to next. So after we've done the prioritization, MnDOT wide, we're really going to continue that training. We need to continue discussions on change management, data management, organizational structure, and then workforce upskilling and training. For our pilot projects, we are going to be rating those pilot projects and work on an implementation plan. And then we need to evaluate. We need to evaluate and learn, scale up where appropriate, communicate the organizational needs to do so. And with that, I'll leave you. This is a good quote, I think, for folks to remember. There's a lot in the media out there, again, of this is the end of work, or it's going to create more work. It's confusing if you start to read too much into it, but really it's about people constantly coming back to people who use AI will be outpacing those who don't. With that, I'd like to say thank you. I don't know if we're saving questions till the end or doing them now, but I'm willing to.
We have a couple of minutes, Melissa. Maybe we could do the last one for sure right now, because it pertains clarifying question to the survey. So a question is, did the survey demographic sample include frontline workers at MnDOT?
It did. We got a pretty good cross section of MnDOT folks. Again, it was only 200 people out of a whole lot, so we did include the survey and sent it out to frontline workers, folks who work out in the field. Definitely a lesser response from some of our maintenance staff. They just have less time in the office and less time staring at it. But working with some of those groups in particular to make sure that the pilot projects we are looking at are considering those folks as well. So trying to work around that limitation while it did get to them.
Great, thanks, Melissa. And yeah, maybe the other two we'll save for the general discussion after the presentations.
Okay, thank you so much.
All right, we'll turn it over to our last presenter, and Qizhi, if you want to take it away.
Thank you. Could you verify you can see my screen?
We can see your screen.
Okay, thank you. Good afternoon, everyone. Thank you very much for having me here. So my name is Qizhi He. I'm assistant professor of the structural engineering in the Department of Civil, Environmental, and Geoengineering. It's my pleasure to share my perspective in this CTS webinar. So my research has been focused on developing AI-enabled simulation tools for complex material modeling and structural mechanics in the past 10 years. So today, as reflected in the title, I will highlight several research efforts in our department and in my group that explore how AI can be integrated into simulation and design for resilient material and infrastructure. I will also talk about a few transportation-related projects that I was involved recently in collaboration with transportation faculties. And the central issue I try to emphasize here in this talk is, despite the exciting success of AI, its adoption in civil and transportation engineering raise an increasing urgent question. How do we ensure and quantify the predictability and the reliability in this safety critical system? So in this sense, I would describe myself as both AI promoter and a critical evaluator. All right, so let's go to the next slide. So to understand the challenges we face with AI today, I would like to use this diagram. We step back and examine how predictive science have traditionally been done. So broadly speaking, there are two fundamentally different paradigms of prediction. The first one is we call physics-based modeling, or Galileo scientist approach. These models are governed by the physical law, such as the conservation of mass, momentum, and energy, and based on which we can predict a complex dynamic system from limited data. You just think about the scientific computing which dominate our modern society in the past 50 years. So on the other hand, over the past decades, we have seen a rapid rise of so-called data-driven AI. This model learn the statistic relation or representation directly from a huge amount of data. They are extremely powerful for learning the high-dimensional system and scale very well when the data set is really large, especially with the so-called modern deep learning architecture, like a transformer, like the right now the latent diffusion model, right? As discussed earlier by Seongjin and Melissa. However, there are a few key weaknesses. They are often considered as like a black box model and struggle when extrapolating to scenario they have never seen. So I would like to point out that interestingly, actually this philosophy is not new. It's date back to like the 16th century when uh, Copernicus already heavily rely on the observation data to simplify the cosmology model. right? So and why we call the scientific computing is because later the Galileo emphasized try to understand the physical mechanism for the prediction. So I would like to say the central challenge in today is how to merge these two paradigms together to help to provide a better and reliable prediction. So, as we already know, AI, we already heard a lot of AI success story everywhere from the AlphaGo, defeated Lee Sedol in Go, and diffusion model, generating the fancy image and ChatGPT and producing the large context. So they are remarkable achievement. But it's important to understand where this system succeed. They mostly operate so-called in the low state environment where errors are acceptable and easily corrected by human. They rely on mass curated data sets and function within a bounded decision space. In many cases, AI perform very well in this like a surrogate for forward inference under this decision. But engineering reality is very different. In transportation or civil infrastructure, prediction error can have catastrophic disaster consequence. This is where engineering alarm the bell rings. We often work with very small data set, and also the data is heterogeneous, and the model are routinely pushed beyond their training domain. So in this condition, AI could hallucinate physically impossible result, and they may even fail silently out of the distribution or express high confidence in some wrong prediction. So I will use this example to illustrate what we call the long tail problem, which means the case where AI fail in rare scenarios that are poorly represented in their training data set. So on the left, you can see this is a very classical computer vision example where we have a lot of data set about panda, but small unusual perturbation in the noise will lead to incorrect yet highly confident prediction is become a gibbon, right? And here this example is from my graduate finite element course. So we asked ChatGPT to compute the nodal force for the Q4 elements on this curve structure. So something we consider should be very straightforward. So you can see the ChatGPT outcome looks mathematically reasonable. But actually, if you take a look, the expression is incorrect. Even I challenging the problem, the model remain confident in their wrong answer. So this is a really interesting problem. This is a silent failure. So in engineering practice, silent failure are particularly dangerous because you don't know. You cannot predict and it just suddenly show up without any alarming, right? So what does it take to use AI in engineering? As we already showed, accuracy alone is not enough. So I believe the following requirement define what we really need for this safety critical AI. First, it should be physical consistency. Prediction must obey certain given conservation law, the given knowledge human already cultivate in the past few centuries. Second, the result should be interpretable. Engineer must understand why the prediction is made. And third, I believe it's usually less attentive to this issue is robustness. So in numerical simulation, we care this a lot. We need to make sure the simulation tool is a convergent, which means that given different scenario, you should predict a reliable prediction. But in AI, this actually is really easy to collapse. That means the model need to handle the uncertainty in model and data, like an extreme geohazard event. It must be controllable even when the prediction or the operation is at the limit of the training data set. So let's now turn to some high consequence prediction cases in civil and transportation engineering. So in this setting, prediction and reliability are essential. It's not optional, it's essential. So prediction error will directly impact the public safety and economic decision. For example, even small error in like a pavement damage prediction can lead to $1 million in maintenance or increased safety risk, right? And this physics-based scientific computing, as you can see here, has been there for a long time and serve as the foundation for this kind of problem. For example, for simulating this like a structure fracture or failure, and also the natural hazards like a landslide and the flood impact, the dam break problem, how the flood impact the infrastructure. And the success of this model is because it tried to capture the underlying mechanics. However, this problem remains challenging. So as you can see here, the data are often still sparse and they are noisy. So and their behavior is strongly depends on this so-called the variability of the surrounding loading and the environment conditions, and also not to mention the material exhibit complex nonlinear behavior. They are usually made by very complex engineering material. And in this scenario, pure data-driven AI struggle because of a lack of this physical understanding. Okay, I would like to further motivate the problem in pure data-driven AI by this 101 course related to civil material, right? This illustrates a common pitfall in material modeling when you just using the simple AI. So we can collect the stress strain data from this so-called tensile test, right, on the metal specimen. And a standard AI regression model may fit the training data set very well, but a lot of studies start showing that it failed to generalize to different loading conditions, as you see on the right-hand side. So why does it happen? Because a lot of material, especially related to transportation and civil construction, like asphalt, soil, or this kind of the metal show here are path-dependent material. And plasticity and damage depends on the loading history need to be well considering. It's not just using the current state can represent the whole behavior, such that the pure regression model cannot capture this behavior unless mechanics is well embedded in the system. Okay, then the question is that how do we address this limitation? And I list here a few emerging topics along this direction, shifting from the so-called pure curve fitting to the predictive science. And my group has been also actively working on this topic. So first we call it operator learning, which try to learn the mapping between the functional space. For example, from the loading history to stress response, rather than just a point-wise prediction. Second is a physics-informed learning, where the physical law, the governing equation, can be introduced in the AI learning pipeline to improve its physical consistency. And third one is a so-called differentiable solver, which you can consider as a framework, including the previous two one. So under this framework, the classical numerical method can be similarly integrate into the training loop for this end-to-end optimization. So this approach, the goal for this approach is to enable stable, physically admissible prediction, not just for good fitting. Okay. So I would like to use this slide to illustrate what we refer to so-called physics-based AI, where we explicitly combine the data-driven model, as you see on the left-hand side, with the physics-based knowledge, which means whatever physical knowledge you know, you can incorporate into the loss function such that facilitate the learning process. So if the model predicts something that violate the physics, for example, for example, Darcy law, right, which represent the conservation of mass. The physics term will penalize during the chaining, and as you can see here, actually can even capture some very non-smooth behavior if you have this additional term. So this approach is especially powerful in engineering, where we often have a strong physical understanding but limited data. Okay. With this physical-based AI, let me use a few examples to demonstrate their effectiveness. So let me first revisit this key application we just mentioned in the previous slide, how to predict the behavior of so-called path-dependent material, such as asphalt, concrete, or soil, where the current response depends strongly on loading history. So as we discussed earlier, conventional AI will fail in this case because this model is a bit so-called like a memory effect arising from the plasticity and damage. However, from mechanics, we know that such a behavior can be rigorously formulated within the framework of thermodynamics. So our group thinking that we can utilize this idea, for example, using this so-called internal state variable to represent the hidden material evolution. So building on this understanding, we develop so-called history-aware neural operator. So Heno is designed to learn the continuous hidden dynamic by combining the spectral operator for this kind of problem. And I would like to show you the result here. As you can see, the results shown here clearly show the advantage of this history-aware approach on the right-hand side, right? So we test the model on this 3D anisotropic damage in the brittle material. Our model consistently outperformed the conventional recurrent neural network, especially under the unseen loading path. And you can see if you purely just try to learn the data, even you using state-of-art recurrent neural network, you still will find out that when you apply to testing data, when you have different condition, you will have a diverged prediction. Okay, so I just want to using this example to show you that respecting the physics of the history dependent play an important role in this AI prediction. We also apply the physical AI to this as for misdesign problem. And this work is led by Dr. Tianhao Yan and also in collaboration with Professor Le and Marostino. And pavement performance extremely depends on the compaction, right? So despite its importance, compaction is not systematic adjust due to a lot of challenging. For example, the high dimensional design space. So nowadays the process is largely still based on trial and errors. And I would like to say is that from the data perspective, this is a classical small data problem. We don't have a lot of data because every test is really money cost and also very time consuming. So this make an ideal case for so-called physics-informed AI, where domain knowledge can be utilized for to enhance the prediction. Okay, so here to adjust that, we use the physics-informed machine learning. We utilize the aggregate arrangement, the physical law of this zero-torus compaction, right? So by embedding this governing physics directly into the learning process, the model is strongly regularized. Even with limited MnDOT data sets, as you can see here, we can accurately predict the compaction curve. Also, we are able to quantify their uncertainty. So I believe this example highlight a key topic of this talk is when data are sparse, and the physics is well understood. Physics plus AI deliver predictions that are not only accurate but also reliable. All right, moving forward, now I want to shift to a transportation-focused application. This is we try to monitor the pavement we try to estimate the pavement quantity by using onboard vehicle data. Especially we focus on evaluate this roughness prediction. So the key point is that we want to using this OBD data to estimate the pavement roughness and in a very convenient way, right? So the graduate student, develop a hybrid CNN and LSTM model architecture. Of course, they need they need to investigate the parameter sensitivity to highlight to single out the important parameter utilized in the model. So right now, finally, we are consider integrate the vehicle speed, orientation, and acceleration. And we can see the model can capture both the spatial feature and the temporal dynamic of the vehicle road interaction. As you can see here, we have a very strong agreement between the predicted and measured roughness value for both training and testing data set. And we also show a few data, field validation here on testing on the Minnesota 36 loop. So we compare our predicted model with the MnDOT high precision reference measurement. The color map indicate the percentage of difference along the roadway. So overall, the agreement is good, and the model captured the spatial variation in this pavement roughness. Although we still observe some like a larger off in particular area. Here I want to highlight that the onboard vehicle data are noisy and influenced by the vehicle dynamic and operating condition. So even we achieve a relative desirable result here, but we still need to consider the uncertainty and bias. This is very important for our future study. All right, so I'm going to wrap up my talk. And looking ahead, I believe the ultimate goal about this physics-based AI is to build infrastructure digital twin. So this digital twin is not pure data-driven model. Their hybrid system can tightly integrate the physics-based knowledge with the AI model. And physics provide, for example, the structure, accuracy, physical consistency, while the data-driven AI provide the speed, the scalability, and real-time inference. So together they can enable a digital twin that can be continuously updated with the sensor data and supporting the real-time decision monitoring and collaboration. And this paradigm have already shown very strong impact in the robotic community, where they need to identify the physics enable the real-time control under this complex environmental interaction. And also in our group's research work on this, try to design a simulation pipeline to optimize the barrier to protect infrastructure from this natural disaster like a flood. So the key message is simple: AI is not a replacement for engineering judgment or physics-based modeling. It's an argumentation allowing us to deploy physics at scale in real time and under the uncertainty scenario. All right. So due to the time limit, I will just skip this one. I just want to point out, generative AI has been a very popular topic nowadays, but we identify there are a few issues in terms of the inverse modeling, and by integrating in physics will be a one feasible solution to address this potential issue. All right. All right, so I will close with this the take-home message. I just want to emphasize again, AI in civil and transportation engineering is safety critical. So failure can be catastrophic, and reliability and physical consistency is matter more than the raw accuracy. And I believe that the combination of the physics and AI will be the key to building a trustworthy and reliable system for the next generation infrastructure. All right. So with that, I will close my talk and thank you for your time. I'm happy to take any questions you may have. Thank you.
Wonderful. Thank you so much. I'm wondering if we might tackle the last question at the moment, and then we can open it up to all the panelists for the other two. So the question is, how do you address overfitting concerns in the inference model when using physics-based solutions to real-world problems?
Oh, this is a very good question. I would like to say incorporating the physics is one motivation is exactly to handle the overfitting problem. Because overfitting to physics actually is a good thing. You just think about like a governing equation, like a conservation of energy or conservation of the momentum. Overfitting to that, that means you can satisfy this equation everywhere, which actually is a means you gain additional stability by overfitting to that. But overfitting to data is dangerous because data the data have finite dimensional you have some space you have no statistic understanding on that, then you may get to the so-called overfitting issue.
Great, thank you. Okay, let's open it up to all panelists for either of these questions. Feel free to jump in. And then if you have additional questions in the audience, feel free to put those in the chat, or you can raise your hand and we can call on you as we're going here. So the question I'll start with is, in your all opinions, how can AI be used to tackle long-standing perpetual issues that seem unable to solve to date? The question lists, like, for example, maintaining ADA levels of pedestrian accessibility after snowfall. But in general, like, how do you see AI being used to tackle long-standing issues that we haven't been able to solve yet?
I can start. I think that that's exactly why we're here, right? There are certain things. I know at MnDOT that the problem was just too large and maybe not worth the time it would take to solve. And we've already solved some of those problems using AI and the capabilities to look at large amounts of data, find errors through machine learning, and then report back. We're able to tackle issues that we previously it just wouldn't have been kind of worth the time, thousands of hours of manpower put into something, or before we could where now we can really tackle those issues. Things like the example that person puts, ADA levels of pedestrian accessibility after snowfall. That's really getting to some of that visual processing that is one of the places we are excited about and talking about. That leads to asset management, being able to look at things like guardrail down, ADA accessibility. If you put a very simple camera on a vehicle that passes that way every day anyway, so mail trucks or maintenance vehicles or whatever they are, they're continually gathering that data. And again, we no longer have to use hundreds of hours of people looking at that data, but a computer can look at it, report back, tell us when there's an issue. So the possibilities here are huge for the things we couldn't typically gather, would rely on a phone call for a pothole or something else. If we have that visual feedback and a computer telling us, hey, there's something doesn't look right here, something doesn't look right here, suddenly we're able to tackle these things more proactively.
Mm-hmm. Other thoughts?
I think Melissa's point is exactly what I was going to answer to this question. So AI is not just a new thing, but it's more like a tool that we can leverage. And then because we have AI, we now have ability to sense more in a more smarter way. So to this question, the exact answer I was thinking was, if we have more camera, and especially now we are entering into the era of like autonomous vehicles, which are equipped with a lot of cameras and sensors, and we have uh, and these sensors are getting cheaper and cheaper. And then if we solve the privacy issues and some regulatory issues associated with those data sharing, then we have access to almost infinite amount of data. And to analyze those data and to use those data efficiently and in an intelligent way, we need AI because human cannot physically run through all the camera. Like MnDOT has like a lot of, I think more than 1,000 cameras on highway from 511. And one of the research question I want to do is, can we scale monitoring those cameras using AI? So AI opens new door to kind of solving problems that we couldn't have solved without AI.
Wonderful. Okay. I might combine two questions together here because I think they're relatable. So a question is, first of all, thanking you all for your reflections about AI. And given your knowledge, how can we help the public understand some of the nuances about AI, including its limits, in the face of just like this relentless promotion of using AI all the time and it being all powerful? And I'm going to add in the question about how does environmental impacts of AI intersect with this work, especially at MnDOT, but in general. And so overall, how would you advise the public and all of us in understanding, what AI can do, what its limits are, with the constant kind of promotion of its use?
Uh, I'm happy to start again. So I think there's a couple of things here. I think some of the programs, some of the things we're looking to use, some of it maybe isn't there yet. I think Qizhi's presentation talks a little bit about maybe it's not ready for everything. There's still issues with some of the things I put out, the risks there. And it's moving so fast that the opportunity is, I think I use the term drinking from a fire hose. Where do we put our efforts? Where do we do, what's our next step? Which is why we're taking it thoughtfully and carefully. Also, as we're working with the public, we don't want to put our services to the public at risk. Big changes can lead to big failures at the same time. So that the thoughtful, measured approach is the best way for us to kind of gather some of these opportunities and bring them together and put them in place in a way that continues to ensure that our ability to serve the public isn't at risk. So coming at this from MnDOT, right, we really want to make sure that we continue to provide quality service, we continue to be responsive to the public's needs, and that doesn't mean taking on every shiny thing that comes our way, but having a measured, thoughtful approach towards what can actually improve our products and services. And doing all of that while we're still delivering our daily products and services at the same time, right? We all have full-time jobs. So I think the with the energy question though, and I think an interesting part of this is, some of the things we're most excited about is like the asset management or that visual detection that we just talked about. And those use a lot of data and a lot of energy. So that is a big data processing, large amounts of visual information coming, large amounts of storage to keep that visual information. There's privacy concerns related to that. So lots of big sticky issues along even with that large amount of data that we're going to be collecting and therefore large amount of energy that it takes. So being aware of kind of where we want to spend our capacity to take on some of those big projects, I think is important, and that measured approach, doing things where it makes sense, to not be overusing any resource, money, energy, time, all of those pieces.
Any other thoughts, Qizhi or Seongjin?
I found there are a few questions, so I'm not sure which
Okay.
one to answer
Yeah,
first.
let's keep going on to some more. So another question is, panelists or the attendees appreciated seeing how AI modeling can be used in physics and for structural engineering. Are you aware of other AI applications in other fields in which formal theory is used as a foundational principle for model building?
Yes. Actually, actually, I would like to take this question. Actually, the physics informed AI right now become really a popular topic, even though some rigorous mathematician engineering already identify some issue along them and try to develop some different paradigm to enhance the reliability. But still, it is widely utilized in even non-STEM, like economy, when they have the I saw some article that using this idea to predict the stock market. They also have some theory like similar to CFD, so they can do that. And so I believe there are quite a lot of this kind of study related to the application you just mentioned.
Wonderful. Maybe in the interest of time to get to the other two, I'll continue to tackle the last two questions. So, regarding generative AI, how do you tackle the issue with reproducibility?
So one thing I can comment on that is, so there are two aspects. First of all, generative AI is trained to be probabilistic. So it is not an issue that it generates something different, completely different from like one instance to another. Second, I think the and kind of continuing on that, like the hallucination in large language model is not an error, it's a feature. Um, but then if we have a good generative model, I'm not saying that current generative models are all perfect and they're all good at everything. But if we have a good generative model that understands what the problem is, then it should constantly give similar output. So for example, if I'm using generative model to predict pedestrian trajectory, it's not outputting something completely different every time because we give previous trajectory of a pedestrian to kind of start from. So it generates a distribution of trajectory based on the previous trajectories. So it's not completely different from one another. But then all of those outputs matter a lot because in terms of like trajectory safety, like intersection safety monitoring perspective, we need to know what are the possible trajectories of a pedestrian and then evaluate whether that's going to create a crash or not. So I hope that answers the question. But right now, if you want to turn off that probabilistic nature and then have reproducible outcome every time you run a generative AI, you can control, especially with large language model, you can control the generation process and then turn the temperature to 0 and then make the model output uh, the same answer every time.
Yeah.
Wonderful.
And
We have 1 minute before we need to transition to kind of our closing. But Melissa, with that, there's just a question that's very specific to MnDOT about um, do you foresee consultants being able to use AI-based solutions in submitted projects? And if so, are there particular tools that you see as becoming standardized in the civil consulting world?
Yeah, good question. I mean, I think for sure we would be allowing for artificial intelligence to be submitted as part of projects and project responses. They need to follow our generative AI standard. It's beyond Copilot. It has more information about what our requirements are right now. And we are reviewing more pieces from kind of a risk-based perspective. So big important piece there is understanding the risk, understanding the benefits, and standardized, here, this is a little bit like asking me to predict the future. I think there are places where AI is shining and has the potential to shine a lot right now. We talked about a couple of them. And I think, as I'm using different products and services, things are just becoming more and more integrated with artificial intelligence already in them. So I can't necessarily predict the future on exactly what would become standardized in the civil consulting world. I'm looking to other industries like the medical profession, the legal profession, which seem to have kind of trained models based on kind of their professions. Will we go that way? Maybe, right? So definitely as interested as everyone else to kind of see where it goes and where the products and services kind of really lead us to, but a lot of opportunity in this space. Just as I discovered as doing the survey, there's just so many things that it could help with. Where it's going to go will to be determined.
Great, thanks, Melissa. All right, I was just given permission to just continue with Q&A. So we're gonna do one more, okay? Before we close. So the last question is, this person can see a lot of value in the usage and application of AI in transportation and environmental engineering. Do any of you see recent examples of transportation planning and AI that you may know of or can point to as good examples of successfully using these tools?
I don't have a concrete example on top of my head, but I guess especially with generative AI, there are a lot of studies related to synthetic population generation, which I'm also interested in it. And there are a lot of uses in transportation planning. One of the example that I'm currently working on with my collaborators in South Korea is that South Korea is facing aging population, and aging population will fundamentally change how travel demand works. Because right now we have a lot of commute demand in rural area, but maybe in the next 20, 30 years, that's not going to happen. And it's going to be mostly travel related to Medicare or more like a entertainment based travels. So my team, so I and my collaborators are working on developing generative AI tool which can predict the spatial and temporal distribution of the travel demand using generative AI, and then considering that this age distribution is going to change in the future, and this kind of I think this kind of research questions are not really possible without generative AI. But because we have these tools, it's actually possible to kind of tackle these kind of questions.
Yeah, I'll also add just there's actually quite a few examples from MnDOT, but some of them we've used video and looked for near miss crash detection, and it would have been literally, you know, dozens of hours of watching video, and now we have AI and machine learning reporting back when we've seen near misses on a high crash corridor. So that was very helpful. We've also had large data sets in which we know there are errors, and AI has been able to report back when the data definitely seems out of whack, and then we can go out and actually fix those systems that are reporting back incorrectly, where before it was a manual process and you're sifting through thousands and thousands of data of spreadsheets looking for that data, and it just wasn't worth the time. And we would wait for a project to come up where we would then find the error. This way we can more proactively address those. So lots of different cases like that where we can kind of start to get to the quality of what we're using, and as well as safety. Yeah, we're already using it and integrating it where it makes sense.
Mm. And if I may, I would like to add, I think we the right question will be more asked about the nature of the AI. There's what kind of problem is really suitable. So as we already discussed, right now we believe the AI is more suitable for when the data is really large. You really have heterogeneous data that, based on the traditional model, is really hard to classify or regress. Then in this case, will be more suitable for AI. And just back to the previous question about generative AI, about the reproducibility. So it also depends on the application, right? In some application, for example, in physics engineering, the inverse problem is ill-pose, but ill-pose will be an issue. But in some problem, the ill-poseness, which means the managed solution, is a feature. So you don't worry about that. So my point is that the power, the effective of AI is really depends on the problem you are interested, and this should be the first question to ask.
Well, with that answer, we are right at time here. So I just wanted to thank all of our presenters today for their time and their expertise, and thank everybody on the call for your questions and good questions and discussion. I'll just put a short plug that, our council at CTS is always interested in identifying what issues people are having related to education and engagement or ideas for future speakers. So if you have any ideas you'd like us to tackle with future webinars or speakers that you think would be great for one of these webinar series, feel free to reach out and let us know. And with that, thank you everyone for your time today, and especially a extra thank you to our speakers.
Thank you.
Thank you.